Okay, so here we go. We have our coefficient matrix that's been augmented with our solutions. And again, our goal is to get row-reduced echelon form. Our goal is to get ones down the diagonal and zeros everywhere else. Now, your first goal should be to get a 1 in this upper left corner. And if there's not a 1 there, then you may have to switch the rows around, and we'll see what that looks like, or maybe multiply by a coefficient, and again, we'll see what that looks like. But we are fortunate to know and have that there's a 1 here, so there's nothing to do. Aha, we've done our first step. What we're going to take this 1, we're going to pivot around that 1 and basically knock out all of these values so they're zeros. And the way we do that is we're going to take a value, multiply it by 1, and add it to each of these rows respectively. So for example, I have a 2 here, and the opposite of 2 is a negative 2. So what I'm going to do is I'm going to multiply negative 2 times row 1, I'm going to add it to row 2, and I'm going to put it into row 2. So that would achieve that to be a 0. Now, again, we're doing everything balanced. We're still following the fact that this came from an equation. So what we do to one side, we have to do to the other. So I'm going to multiply this first row by negative 2 and then add it to the second row to make that a 0. The only row that gets changed is the row that you're putting it into. So even though I'm multiplying row 1 by negative 2, that's not changing row 1. I'm only going to change row 2 because that's the linear combination that I guess I'm changing it to. So row 1 remains the same. 1, negative 1, 1, 8. Row 2 now becomes negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times negative 1 is 2 plus 3 is 5. Negative 2 times 1 plus, negative 2 times 1 is negative 2, plus negative 1 is negative 3. Negative 2 times 8 is negative 16, plus negative 2 is negative 18. Now, when you get good at solving these row operations, you can do 2 separate rows simultaneously. Right now, nothing has changed in row 3. My linear combination has only affected row 2. So if I can do something with this row 1 to simplify row 3, I'm going to do that in another step. So maybe under here, I could say, well, wow, I could make that a 0 if I had a negative 3 that I added it to that 3. So I'm going to take negative 3 row 1 and add it to row 3. I'm going to put the result into row 3. So negative 3 times 1 is negative 3, plus 3 is 0. Negative 3 times negative 1 is 3, plus negative 2 is 1. Negative 3 times 1 is negative 3, plus negative 9 is negative 12. Negative 3 times 8 is negative 24, plus 9 is negative 15. And this is now my reduced matrix. It's not row-reduced echelon form. I don't have 1s down the diagonal, but I do have a 1 here, and I've cleared the bottom column by making them zeros. Now, again, my next goal, after you've gotten this to be a 1, my next goal is to make this a 1 right here. And I want to make this a 1 by either multiplying, I could multiply this whole row by 1/5, because that would give me a 1. But the thing is, that would also give me fractions here. And not that that's bad, but for every fraction you have here, that will carry to the next step and to the next step. So if there's a way I can avoid that, I would love to do that. I have a 1 here, and would certainly be nice if that 1 were up here. Well, one of the things you can do in this row reduction is switch rows. Because if you think about it, the order that your equation started was arbitrary. It doesn't change it if you take the first row and make it into the second row and just switch the rows. It has no bearing on your final outcome. So what I'm going to do is I'm going to switch row 2 with row 3. And my work, I still have to tell, here's what I'm doing. So I'm going to switch row 2 with row 3. It's a row swap. Notice row 1 remains the same. So row 1 will still be 1, negative 1, 1, 8. The new row 2 will now be 0, 1, negative 12, and negative 15. And the new row 3, since these switch, will be 0, 5, negative 3, and negative 18. Okay? And so now I have 1, zeros down below, 1. Now my next step is to knock out above and below and make those into zeros. And it's kind of the same procedure. Is you get a 1 in place, and then you pivot around that 1, meaning get zeros everywhere else. So we're going to do the same technique that we did up here. We're going to pick this opposite, and pick this opposite, and do a linear transformation on row 2 into row 1, and then into row 3. So in this particular case, since they're already opposites, I'm going to do 1 row 2. I'm going to add it to row 1, and I'm going to put the result into row 1. The fact that I'm putting the result into row 1 tells me that that's the only thing that's going to get changed. So 1 times 0 is 0, plus 1 is 1. 1 times 1 is 1, plus negative 1 is 0. 1 times negative 12 is negative 12, plus 1 is negative 11. 1 times negative 15 plus 8 is negative 7. We have not changed row 2. Row 2 does not change, all we're doing is changing row 1. So I'm still going to keep 0, 1, negative 12, negative 15. And then I can certainly change row 3 by multiplying a coefficient by 1 that would knock out this that would knock out this 5, and that coefficient would be negative 5. If I do negative 5 row 2 and I add it to row 3, put the result into row 3, that will give me the desired 0 here. So negative 5 times 0 plus 0 is 0. Negative 5 times 1 plus 5 is 0. Negative 5 times negative 12 is 60, plus 3 is negative 57. And then negative 5 times negative 15 is 75, minus 18 is negative 57. So, the advantage of starting with this being a 1 and making everything zeros is that when you do subsequent operations, your zeros remain. The worst thing can happen is that you do things in a random order and you made it 1, 0, 0 here, but then all of a sudden you did something where this becomes a non-zero, and now you've got more work to do because you have to change those back to zeros. Okay, so we're getting close. We have 1, 0, 0, 0, 1, 0. Now our next step is to move down the diagonal and make this guy right here a 1. And when he's the only one left, the best thing to do is just to multiply both sides of the equation, or this entire row, by a constant. And that constant would be whatever would make that equal to a 1. And since this is negative 57, the thing we can multiply both sides, or this entire row by, is the fraction negative 1/57. So what I'm going to do is I'm going to change my matrix and augment it by multiplying negative 1 over 57 times row 3, and it's going to stay into row 3. Row 1 and 2 are not changed. So 1, 0, negative 11, negative 7. 0, 1, negative 12, negative 15. 0, 0, 1, because negative 1/57 times negative 57 is 1, and then this is a 1. Okay, now we're at a point where we can actually solve this through back substitution, because I know this equation right here tells me that 0x plus 0y plus 1z equals 1. In other words, z is 1. And once you know z, you could back substitute it into this equation and solve for y, and back substitute in that equation to solve for x. So you really have to look at the directions. Does it ask for row reduced echelon form, or is it just asking to solve the equation? And in this, like I said, in this case, I'm going to try to do row reduced echelon form, so I'm going to pivot around this 1. I'm going to take this 1 and transform those above it into zeros. And again, we've already made these zeros, there will be no effect. They won't change anything above here because I did it in the right order. And again, the right order is to start with the top 1, knock out zeros. The next one, knock out zeros. The next one, and then knock out zeros. So I'm going to do one more matrix transformation. I'm going to take this and add it to row 2 by multiplying row 3 by 12. 12 of these plus that will knock this out. So it's 12 row 3 add to row 2, and you're going to put it into row 2. And so let's see what happens. Row 3 remains unchanged. Maybe, yeah, that should be okay. So 0, 0, 1, 0, oops, 1. Okay. So then 12 times 0 plus 0 is still 0. 12 times 0 plus 1 is still 1. That's the point of doing it in this order. 12 times 1 is 12 plus negative 12 is 0. 12 times 1 is 12 plus negative 15 is negative 3. And then we want to get this simplified to a 0. So the row operation would be 11 of these, 11 row 1, and add it to row, 11 row 3, and add it to row 1. 11 row 3, add it to 1, and we're going to leave it in row 1. So again, 0 times 11 is 0, plus 1 is 1. 0 times 11 is 0, plus 0 is 0. 0 times 1 is 11, plus negative 11 is 0. And then our last guy right here, 11 times 1 is 11, plus negative 7 is 4. We have row-reduced echelon form. And if we read this, it says 1x plus no y plus no z equals 4. So I know x is 4. This row says no x's plus 1y plus no z's equals negative 3. So y equals negative 3. This row says no x's plus no y's plus 1z equals 1. So here's a list of our solution. It may also ask us for an ordered triple. So you put them in order, alphabetical, 4, negative 3, 1 is the ordered triple. Okay. Like I said, the advantage of doing something like this, yes, it is tedious, and there are multiple steps you are doing, and it's a little bit cumbersome at the beginning, but the advantage of this is you can come up with a systematic way to solve an equation. And there's nothing special of the fact there are 3 variables and 3 equations. This works if there are 4 variables and 4 equations, 5 variables and 5 equations. Your technique is the same. You go 1 down the diagonal. And the idea is that if you have a systematic way, an algorithm, or a process to solve these, now you can take and you could use technology to set up a program, to set up a way that you can input the data, and each coefficient has a significance in terms of its order, and you can crunch the numbers and come up with a solution very systematically. So we will practice the process, we will practice the operations, but then obviously we won't always do them this way. We'll find other ways and efficient ways to solve these, but this is one way to solve a system of equations using what's referred to as Gauss elimination, which you get to row-reduced echelon form.